So number 50, we have 16 to the 1/2. For this, you should remember the exponent rule. X to the a over b is equal to the bth root of x to the a. In this case, we have 16 to the 1/2 is equal to the square root of 16 to the 1. In other words, just square root of 16, which is 4. 51, we have 125 to the 2/3. This is a great one because it highlights a really important point, which is the following. Ordinarily, we write the fractional exponent rule this way, the way that I just did a second ago. X to the a over b is the bth root of x to the a. But there's actually a different way of writing this, which is the following. We can instead write this as the bth root of x all to the a. The difference between these two expressions is that here I'm taking x and raising it to the power of a, and then afterwards taking the bth root. Here I'm taking the bth root first and then raising the result to the 8th power. So it's the same two operations, 8th power, bth root, but I'm doing them in different order. And what I'm saying here is that you can do those two operations in either order, and in some problems, like this one, for example, it's much easier to actually do it this way, to take the root first and then raise to a power. Because, you know, if I tried to do it this way, I would have to square 125, which is annoying, that's a large number, and then I would have to find the third root of a very large number, which is probably something that I wouldn't know. I don't know many third roots. On the other hand, if you start by taking the third root, you're going to get a much smaller number, and then when you square it afterwards, that's going to be a lot easier. So let's take the cube root first and square afterwards. So cube root of 125 is actually just 5, and then 5 squared is 25. Voila. 52, we have 64 to the 2/3. That's pretty much the same kind of problem that I was talking about before in the previous problem. I think it's a lot easier to begin by taking the root and then square afterwards. Cube root of 64 is 4, and then you square that and you get 16. 53 is 25 to the negative 1/2. This exponent here is both fractional and negative, so we're going to need to use both the negative and the fractional exponent rules to evaluate this. The fractional exponent rule I have right here, or if you like, right here. The negative exponent rule is that x to the negative a is equal to 1 over x to the positive a. So what I like to do when I have an exponent which is both fractional and negative is I like to take care of the negativity first. Like I need to deal with the fact that it's a negative exponent first. So 25 to the negative 1/2 is 1 over 25 to the positive 1/2. So now I've dealt with the fact that I had a negative exponent. Now I'll deal with the fact that I have a fractional exponent. 25 to the 1/2 just means square root of 25. So this is 1 over root 25, which is just 1 over 5. 54, we have x to the 1/2 times square root of x. To evaluate this, I would rewrite the square root of x using a fractional exponent. So square root of x is actually just x to the 1/2. And now if I have x to the 1/2 times x to the 1/2, that's actually going to be x to the 1/2 plus 1/2, which is x to the 1, which is just x. 55, we have square root of x to the 16 over 16. So I would say first of all, the large square root can be interpreted as like an exponent of 1/2. So taking the square root of that fraction is the same thing as raising that fraction to the 1/2 power. Then I would recall that exponents distribute over fractions, like you can distribute them to the top and the bottom of a fraction. I guess I'm using the exponent rule like a over b to the c is equal to a to the c over b to the c. I suppose that's the rule that I'm using here. So if I distribute that exponent of 1/2, I get x to the 16th to the 1/2 divided by 16 to the 1/2. In the numerator, I have a power of a power, like x raised to the 16th raised to the 1/2. The exponent rule that you want to be thinking about for that situation is this: a to the b to the power of c, that's like a power of a power. You multiply the exponents in that instance. So that's a to the power of b times c. So in the numerator, I have x to the power of 16 times 1/2. The denominator, I guess I'll take care of that as well. 16 to the 1/2 just means square root of 16. So in the numerator, I have x to the 16th times 1/2, which is x to the 8th. And in the bottom, I have root 16, which is 4. 56, I have the cube root of 27 x to the 9, y to the 3rd. So I would say that there's a couple of things here. For one thing, you might think of it this way. Certainly, you could say to yourself, taking the third root of something is like raising it to the one-third power. And then you could argue that we can use the exponent rule, a times b to the c is equal to a to the c times b to the c. In other words, exponents distribute over multiplication, and that's what we have here inside parentheses. We have several things, the 27, the x to the 9th, and the y to the 3rd being multiplied, and so this exponent 1/3 is going to distribute over that multiplication. So you get 27 to the 1/3, x to the 9th to the 1/3, and then y to the 3rd to the 1/3. What is 27 to the 1/3? Well, taking the 1/3 power of something just means taking the cube root of it. So that's the cube root of 27, which is 3. And then here we have x to the 9th to the 1/3. That's a power of a power, just like we had here. And so you're going to multiply those exponents. So that's x to the power of 9 times 1/3, which is actually just 3. And then likewise, y to the 3rd to the 1/3, that's another power of a power. That's 3 times 1/3 is going to be 1. In other words, so y to the 1, that's just y. That's one way to think about this. There's kind of a different way of thinking about it, but I don't think I want to get into it here. 57, we have the cube root of x to the 12th, y to the 6th over 27. Once again, I would just sort of say that taking the cube root of this big expression is the same thing as raising that expression to the power of 1/3. So I would just begin by rewriting the cube root as a power of 1/3. And then basically what's going to happen is that 1/3 is going to get distributed to everything because, as I mentioned earlier, there's an exponent rule which says a over b to the c is equal to a to the c over b to the c. In other words, exponents distribute over fractions, like to the top and the bottom of the fraction. So we're going to raise both the top and the bottom of this fraction to the 1/3 power. But then in the numerator, I can distribute that exponent of 1/3 a little bit further because once again, exponents distribute over multiplication as well. So if you have two things being multiplied raised to a common power, you can distribute the exponent. So that's what I'm going to do here. So I have x to the 12th, y to the 6th, and each of those is going to be raised to the 1/3 power. So I'm distributing that 1/3. And one more line and I think we'll be done. So here I have a power of a power, x to the 12th to the 1/3. In that circumstance, just like I have here, you're going to multiply those exponents. So 12 times 1/3 is 4. And then likewise here, 6 times 1/3 is 2, so we get y squared. In the bottom, 27 to the 1/3, well, taking something and raising it to the 1/3 power just means taking the cube root of it, and the cube root of 27 is 3. So there we have it. 58, we have square root of x times the 4th root of x times the 8th root of x. I would start by rewriting each of these factors using fractional exponents. The square root of x is x to the 1/2. The 4th root of x is x to the 1/4, and the 8th root of x is x to the 1/8. So when we have something like this, we have an expression like x to the a times x to the b, and if you remember the exponent rule, you add the exponents in that circumstance, right? So I'm going to use this rule right here to rewrite this expression. This is really just x to the power of 1/2 plus 1/4 plus 1/8. Of course, to evaluate that, I need to obtain common denominators. I think the common denominator here is going to be 8. So 1/2 is 4 over 8. 1/4 is 2 over 8. So adding those three fractions together, I get 7 over 8. That's basically okay, except you'll notice that we ask you to, like, your final answer shouldn't contain any fractional or negative exponents. So I need to rewrite this without using a fractional exponent. And I'm just going to use the fractional exponent rule, which says that x to the power of a over b is the bth root of x to the a. So this guy here is really just x, it's the 8th root of x to the 7th. 59, we have, I know people are going to look up the answer to this one. I remember this problem, and people always have trouble with it. So it's y to the 1/2 times y to the negative 1/2 plus 2y to the 3/2 minus 1 over y. Yeah, it's a hard problem. So there's a few things going on. Big picture, what's happening is this y to the 1/2 needs to be distributed inside the parentheses. So it needs to be distributed to this guy, and it needs to be distributed to this guy, and finally to that guy. So we can do that. So I have y to the 1/2 times y to the negative 1/2 plus y to the 1/2 times 2y to the 3/2 minus y to the 1/2 times 1 over y. So we've distributed that y to the 1/2, but how do you simplify each of these terms? Well, some of them are easier than others. This first one, obviously, you just add those two exponents together. That's y to the power of 1/2 plus negative 1/2, which is just 0. Okay. So in the next line, I'll replace that with a 1. This term here might seem a little strange, but remember, like, this 2 here is really a coefficient. Like, in this term, we actually have three things being multiplied. This really just means 1/2 times 2 times y to the 3/2. Like, it's those three things being multiplied together. And the thing about multiplication is the order doesn't matter. Like, we can multiply these three things in whatever order we like. So I'm perfectly free to multiply by the 2 first. Like, it's allowed to just change the order of these things. and put the 2 out front, which is definitely more conventional. Like, we typically write coefficients at the beginning of a term. So I'm going to go ahead and do that. And then I think now that I've rewritten it, it's a little bit more obvious what's going on. Like the y to the 1/2 times the y to the 3/2, you're just going to add those 2 exponents together. I'll do that in the next line. The third term is a little bit more mysterious. Like, how do you deal with these 2 things? There's a couple ways you could do it. I think the most natural way is probably to just rewrite the 1 over y using a negative exponent. 1 over y is the same thing as y to the negative 1, right? I mean, just a quick explanation on that, because y to the negative 1 is 1 over y to the positive 1, which is just 1 over y, right? So I think in the next line I'll basically be done. Y to the 0, that's 1, plus 2 times, now these 2 guys, I'm going to add those exponents. 1/2 plus 3/2 is 4/2, which is just 2. And then here, again, I'm going to add those 2 exponents. 1/2 minus 1 is negative 1/2. So I have minus y to the negative 1/2. And this is pretty good, but again, we do ask you to like not leave any negative or fractional exponents in your answer. So I need to rewrite that last term. So this last term is a little bit tricky because the exponent is both negative and fractional. I would start by dealing with the fact that it's negative, right? Like the negative exponent rule says that x to the negative a is 1 over x to the positive a. So I would apply that. So y to the negative 1/2 is 1 over y to the positive 1/2. And then in the next line, I would deal with the fact that you have a fractional exponent, right? Y to the 1/2 really just means the square root of y. So I'd say that's a pretty good answer. By the way, sometimes people wonder, do you need to rationalize this? Like there's a square root in the denominator? I would say no. The rule that certainly like I follow, and I think that most teachers follow, is if you have a numerical expression, like 2 over root 5, that's a numerical expression. If you have the square root of a number, we would expect you to rationalize that. So I would rationalize that, multiply top and bottom by root 5 and get 2 root 5 over 5. So you should rationalize that. But if the root expression in the bottom is like a variable expression, like 3 over root x or something, you are under no obligation to rationalize that. In fact, I think very few people would rewrite this, right? Like if you multiplied top and bottom by root x, you'd obtain this expression here, but I don't. Most people will not do that, and they'll just leave it this way. So that's sort of the explanation of when we expect you to rationalize. 60. This is pretty much the same as the previous problems. The only difference is it's a bit more complicated and it's multiple choice. So 60a, we have the 5th root of x to the 5th, y to the 3rd, over xy to the negative 2/5. It's pretty complicated. I would probably start by rewriting that radical, that root, that 5th root, as a power of 1/5, right? Taking the square root is like raising to the 1/2. Taking the 3rd root is like raising to the 1/3. Taking the 5th root is like raising to the 1/5. And I wouldn't even do anything with the denominator just yet. Next, I would distribute that exponent here of 1/5. Like I'm essentially using this exponent rule here, which is like ab to the c is equal to a to the c, b to the c. Sort of just using the fact that exponents distribute over multiplication. So that's going to be x to the 5th to the power of 1/5 times y to the 3rd to the power of 1/5. I'm not going to do anything with the denominator just yet. And then finally, here I have a power of a power. So I multiply those exponents. 5 times 1/5 is just 1, so it's x to the, well, 1. You can write the 1 if you want, but that's just x. And then y to the 3/5, xy to the negative 2 over 5. And now I think finally I would start thinking about how the denominator plays a part in this expression. So for one thing, I have an x to the 1. Well, actually, let me deal with the negativity of that exponent there. So anytime you have a negative, have we talked about this already earlier in this review? I don't remember. Yeah, we have. Cool, good, right. So I won't re-explain it. So this guy here, the negative exponent, if you have a negative exponent inside of a fraction, that term sort of just moves, right? So that y to the negative 2/5 is going to go upstairs, but the exponent becomes a positive 2/5. Okay, so I would argue probably next I would combine the two y terms. You have y to the 3/5 times y to the 2/5. You would add those exponents. 3/5 plus 2/5 is 5/5, which is just 1. So it's like x, y to the 1, which is just y, right? You can write the 1 or not, it doesn't matter. And then finally, I would say there's cancellation. The two x's cancel, and you just get y. So evidently, it's just this guy. Assuming I didn't make any mistakes. It's a pretty complicated problem. The 60b is going to be a similar kind of story. Oh, except it says circle all that are correct. Oh, great. Cool. So apparently there's more than one answer. Probably. Okay. Well, okay, so I think I would start by rewriting that fourth root as a fractional exponent. Then I would move that y to the negative 1/2 downstairs. Or, no, I think I'll leave it there for now. There's more than one way of doing these things, but I think I'll distribute this power of 1/4 next. So I have 16 to the 1/4, and then x to the 10th raised to the 1/4. You know, that's like this, right? But you would multiply those exponents. So 10 times 1/4 is just 10 over 4, which can be reduced, and I guess I will reduce it, but in the next line. Okay, so what next? So a couple things. First of all, 16 to the 1/4, that's the fourth root of 16, which I think is 2. 2, 4, 8, yep, so that's 2. Second of all, x to the 10 over 4, that fraction can be reduced. Like 10 over 4 is the same thing as 5 over 2. And finally, this y to the negative 1/2 is going to go downstairs, and the negative 1/2 is going to become a positive 1/2. Next, I would say 20 over 2. I mean, yeah, there's a bunch of other stuff in this fraction, but like you can sort of pretend it's not there when you're reducing. 20 over 2 is just 10. So I think this guy simplifies to 10 over x to the 5 over 2, y to the 1/2. So that's pretty good. The only thing I would add is that, like, you know, once again, we're not supposed to have fractional exponents in our final answer. So, like, x to the 5 over 2, you could call that the square root, which we don't usually write the 2. It's just the square root of x to the 5th. And then times y to the 1/2 is just square root of y. So this is a very good answer. Like, that's definitely a perfectly acceptable answer. But it's not, like, listed anywhere. So what's going on? So, first of all, you know, when you have one square root times another square root, that's the same thing as just, like, taking the square root of the product of the two things on the inside. Technically, that's actually an exponent rule. Like, because, you know, I mean, like, root A, root B. What I'm claiming here is that root A times root B is root AB. The reason for that is, like, these are actually just exponents, right? Like, that's the same thing as this. Anyway, long story short, the denominator here can be written in that way. Is that any of the answers? No, not quite. I'm pretty sure that it's not A. I don't know where you would get 80. I'm also pretty sure that it's not this, unless like I made a mistake somewhere. I don't see how you'd get a 5. Oh, here we go. So C is definitely what we have. So C looks right to me. But you know, they say this thing of like circle all that are correct, so like maybe there's an alternative way of writing it. This looks promising. I actually think that that's equivalent to what we have. You know, because when it comes to simplifying radicals, like square root of, for example, 50, you could rewrite root 50 as 25 times 2. And then what you do is, you know, you essentially take the perfect square out of the radical, and when you do so, you take the square root of it, so that gives you 5 root 2. You can do the same thing with an expression like x to the 5th, because you can rewrite x to the 5th as, or maybe I should just write it this way. You can do the same thing with the denominator of our current expression, because we have x to the 5th y. Let's just think about that denominator, okay? X to the 5th can be rewritten as x to the 4th times x to the 1, or just x times y. Now, why would you do that? Why would you rewrite it that way? The reason why is that x to the 4th is a perfect square, which means I can pull it outside of the radical. Of course, when I do so, I have to take the square root of it. So when I take x to the 4th outside of the radical, I take the square root of it. What is the square root of x to the 4th? Well, it's x squared, right? Like if you square x squared, you would multiply the exponents and get 4. So that's equivalent to D. So it looks like C and D. Okay. Cool, we're moving on to 61. Rewrite each expression without using fractional or negative exponents. Cool. So we have 61 is 2x to the negative 1/3. Remember that this negative 1/3, this exponent is only being applied to the x. By default, exponents only apply to the thing directly in front of them. So the 2 is not affected. So this is like 2 times 1 over x to the 1/3, or if you like, just 2 over x to the 1/3, right? I mean, essentially, this guy, because it has a negative exponent, it's going to go into the bottom of the fraction. There currently isn't a fraction bar at all in this expression, but one is kind of created. And then the x to the 1/3 goes into the bottom. And then that's the same thing as 2 over cube root of x. So that's 61. 62, we have a very similar expression, except with the parentheses, now this negative 1/3 is being applied to the 2. It's being applied to everything inside of there. So you could do this in a couple ways. You could write this like this. Like you could distribute the negative 1/3 to each of those terms separately. I think I'd actually prefer instead to view it this way. You have a single object, 2x, being raised to a negative exponent. So what I do is I take 1 over that object raised to the positive version of that exponent. Okay. And then there's not really anything else to do except to say, well, raising 2x to the 1/3 is the same thing as taking the cube root of 2x. So that's certainly one way of doing that. 63 is negative quantity 2x to the negative 4/3. Not very different from the previous problem, except there's this minus sign here. How does that interact with stuff? The answer is it really doesn't. Like the minus sign here is not affected by this exponent at all. If you like, this minus sign, you can think of it as a multiplication by negative 1, and this exponent is only being applied to the object directly in front of it, which in this case is this guy right here. It's not affecting the negative 1 at all, so like it's just not affecting the minus sign. In other words, like the minus sign just kind of gets carried along for the ride. So I'll just write minus and then a fraction bar. So I have this object 2x being raised to a negative exponent. So what that means is I do 1 over that object raised to the positive version of that exponent. Yeah, and then it's just a matter of applying the fractional exponent rule. 2x to the 4/3 is the same thing as third root of 2x to the 4th. Notice that both the 2 and the x are being hit by that 4 there. I would simplify that a little bit more. I think you can distribute that 4 and say this is 2 to the 4th, x to the 4th. Of course, 2 to the 4th is 2, 4, 8, 16. So 16 x to the 4th is probably what I would write. You could like do the usual thing where like, I don't know, you sort of say, oh, like x to the 4th can be thought of as x to the 3rd times x, and then you can pull this x to the 3rd outside of the radical and do that. But like, who cares? Whatever. Like, I think that's good enough. True or false? Okay, fun. Should I stop here? No, I don't know. Maybe I'll do a little bit more. Okay, so true or false? Use real numbers to support your answer. This is false. Most values that you pick just will not work. Exponents don't distribute over addition. Okay, they don't. I think that's a pretty simple one. This guy here, that's false. You might wonder what this is even saying. The idea here is that if you repeatedly raise something to a power, it sort of matters how you group things. So here's my question. Are these two expressions the same? Put a question mark there because we don't know. They're actually not. So what I'm saying here is first raise 2 to the 3rd power and then raise the result to the 4th power. So what is that? Well, 2 cubed is 8. So 8 to the 4th, right? What is 8 to the 4th? It's a pretty big number, right? It's 4,096. But what about the right-hand side? Well, the right-hand side is, first, we need to simplify the expression in the parentheses. The 3 to the 4th is already a pretty large number. 3, 9, 27, 81. So the right-hand side is 2 to the power of 81. I'm not going to bother even typing that into my calculator because it's such a large number that it's probably bigger than the number of atoms in the universe. Like, I don't know what number that is, but it's a lot bigger than 4,096. So these two expressions are definitely not equivalent, and this rule is not true. The left-hand side of that expression, by the way, the a to the power of b to the power of c, that is an expression which can be simplified as just a to the power of b times c. We would multiply those two exponents. The right-hand side, though, a to the power of b to the c, grouped that way, just can't be simplified. So yeah, it's sort of a weird quirk. I wouldn't worry too much about this one, but it's worth checking out. So I think I'll stop here.